Ever wondered how movies craft those seamless 3D worlds, or how video games make objects bend and break in real time? Today, we're diving into a breakthrough that's rewriting the rules, a revolutionary method to edit 3D scenes as effortlessly as you'd adjust a photo. Let's break down how this works, and why it's a game changer for creators, scientists, and anyone who loves digital worlds. At the core of this innovation is Gaussian Splatting, a technique that uses tiny, glowing 3D particles called Gaussians to represent scenes. Think of them as microscopic, squishy blobs that encode position, color, size, and even a confidence score about their placement. These particles are computationally efficient, allowing rapid rendering of complex environments. But here's the problem. Traditional methods struggle to edit these scenes. Want to move a chair or simulate a fabric draping? You'd have to rebuild the entire scene from scratch. Enter GENIE, the star of our story. This system merges Gaussian splatting with neural networks, creating a smarter, more flexible 3D model. The secret sauce? Splash grid encoding, which ties features to Gaussians themselves rather than a static grid. Imagine a dynamic map that updates in real time as you manipulate objects. No more guesswork. Here's the magic. When you want to edit a scene, GENIE employs Ray-Traced Gaussian Proximity Search, RTGPS, to pinpoint the most relevant Gaussians, like a spotlight highlighting the right particles. It then interpolates their features, blending coarse and fine details to create a smooth, editable representation. This means you can tweak a single object, like making fabric fall onto a cup, and see changes instantly without re-rendering the whole scene. What truly sets GENIE apart is its physics-based editing. The paper demonstrates simulations where leaves fall, cloth drapes, and objects deform, all while preserving ultra-high detail. This isn't just about aesthetics, it's about control. Artists and engineers can now experiment with 3D environments as fluidly as they'd edit a 2D image. The team tested GENIE on challenging datasets, from synthetic scenes to real-world 360-degree environments. Compared to methods like GENIE, RF, and GS, GENIE matches top-tier reconstruction quality while adding unprecedented editing capabilities. Its neural network foundation allows it to learn and adapt, improving with every tweak. How does GENIE balance detail and speed? It uses ~1 million Gaussians, enough for fine textures, but each only interacts with its 32 closest neighbors. Think of it as a 3D pixel grid where each point checks in, with its 32 closest peers to refine shape and color. This local connectivity avoids the computational slowdowns of brute force methods, making it ideal for real-time applications like VR and AR. Researchers evaluated GENIE using 3 key metrics. 1. PSNR, peak signal-to-noise ratio, measures clarity, higher numbers mean sharper details. 2. SSIM, structural similarity index, compares how closely the 3D scene matches reality. 3. LPIPS, learned perceptual image patch similarity, assesses how natural the scene looks to humans. On datasets ranging from chairs to cityscapes, GENIE outperforms older methods in realism and efficiency, proving that smart math beats raw power. So what's next? This tech could transform virtual production, augmented reality, and even scientific simulations. Imagine sculpting a 3D world with a few gestures, or testing architectural designs in real time. The future of 3D creation isn't just more powerful, it's smarter, faster, and more intuitive. Thanks for watching. Stay curious, and we'll keep unraveling the science behind your favorite tech.